I'm going to explain to you now how the interconnections to the Optoscan controller rack work, how the Optoscan microprocessor processes the signals, generates the illumination protocols, and how that is passed on to the data acquisition system. So we have the rack. We have two connections coming from the microscope. We have the high voltage supplied to the photomultiplier, which we connect to the high voltage power supply, and this has got a shrouded stainless steel connector designed to pass the high voltage. We then have a second standard BNC connector which we feed into the input of the amplifier. If we're running a calcium protocol, then we would typically be using Fura2, which is excited differentially at 340 and 380 nanometers to get corresponding high and low calcium signals. We may also monitor a signal at 360 nanometers to get an isospastic point where the signal is independent of calcium concentration. So to set a program, we enter the first menu item from the Optoscan controller, set wavelengths and times, and then we set up, in one of the four programs, we set up however many positions we require to run the program. In this instance, I've programmed up 340 nanometers with a 15 nanometer bandpass for 10 milliseconds, 380 with a 6 nanometer bandpass because the signal is much brighter, and we're using a non-UV lens on the microscope, so the signal from 340 will be attenuated by that. So we're using a much smaller bandpass to compensate for the brighter signal at 380. For 20 milliseconds, 360 the notional isospastic point of Fura2 for 30 milliseconds, and 470 as people would often be looking at a secondary probe, a GFP or something to get, and would be interested in the light fluorescing from blue illumination as well as UV. So we have these four positions in the protocol. The other possible four positions are deselected, so they've got an N by them. So this program will run 340, 380, 360, 470 for 10, 20, 30, 40 milliseconds respectively. So we then go to the third menu option, which is Run Wavelength Program. And if we run, the default mode is for the program to run continuously until it's stopped, so we can stay with that. We're running program 1, which is the one we've set up, and we go to Run Program. So the clicking you can hear is the three galvanometers in the Optoscan moving, one of them to set the center wavelength and two to set the input and exit bandpass respectively. So the clicking away is the slits opening and closing and the diffraction grating rotating to change the wavelength that is projected into the liquid light guide into the microscope. So if we want to look at the signal coming from the amplifier to see what's going on, we connect a BNC output from the primary amplifier into a spare channel of an oscilloscope. I've already set up the oscilloscope to trigger automatically because it makes it easier to show. But the signal we're interested in is on channel 2. So at the moment we have a piece of white paper on the stage. That's a good fluorescent source for testing the system. It fluoresces well in the UV and blue. And we have a green emission filter, so we're not seeing any of the excitation light, we're only seeing the secondary fluorescence. So if we turn up the photomultiplier amplifier, you'll see these profiles appearing on the oscilloscope. And these profiles correspond to, there we go, they correspond to the individual channels in the program. So you see I've set them for 10 milliseconds, 20 milliseconds, 30 milliseconds and 40 milliseconds. There we can see two of them on the same chart. And what happens is the amplifier integrates during the period that the light source is in the the light source is active at that wavelength. So the amplifier integrates the signal, and the peak signal is then stored in the system for recording from the detection acquisition software. The beauty of this system is that the acquisition software does not need in any way to be synchronized to the Optoscan controller. The signals here are available continuously. So here we see the integrated outputs, and we set the first channel to be 10 milliseconds, so you can see the shortest value is the 10 millisecond value. So if we turn the photomultiplier power supply up, so we get that to 1 division, then if we look at the signal on the first output amplifier, we see that corresponds to the peak of that signal. The second one we see is at this point. The third one is off the top of the scale at the moment, so it's up here. And the fourth one is the longest one, which is right down here, because the paper is not fluorescing as well with 470 nanometer light.